good morning, good afternoon, good evening if you're joining from Eastern time zones. And welcome to the webinar of boosting Kafka performance in a day. And obviously we mean Apache Kafka. Before we start, let me introduce myself. And Zoom did a great job. It said that I'm John Ceccarelli, but I'm actually not John Ceccarelli. That's my colleague. So my name is Jiří Holusha, and a little something about me. I'm a nerd. Although I possess the product management job title, I'm a nerd who loves Java. I love compilers and deep level performance stuff. And as I'm from the Czech Republic, I also love beer, and that's all you really need to know about me. So my name is Jiří Holusha, and that's where the special letters come from, because we made it up in our alphabet in the Czech Republic. But we're not here for me. We're here to hear about how do we address Kafka pain points, and what are those pain points. So when we run Apache Kafka clusters, we are typically thinking of three major pain points, kind of performance-wise or operational-wise. The one is speed. By that, I mean how many transactions it can process in a unit of time, operations per second, number of operations in a day, how many of those the cluster is capable of processing while keeping reasonable latencies. Usually this performance metric is referred to as throughput. Since we're talking about typically real-time systems, right, where the response times matter, we also typically are concerned about long response times, about how long does the event, how long do the individual events take to process from the client sending it to a consumer receiving it, right? Sometimes the response time is referred to as latency, and I'm going to refer to this metric as interchangeably, response time latency. And in the end, it's all about how much money you spend on running your Kafka infrastructure. Because in nowadays, you can provision another pair of machines from the cloud. So really, the performance problems are really cost problems as well, right? If you need better performance, handle more transactions per second, the distributed systems are constructed in a way that if you add more machines, you get more capacity. So it's also about how much money you spend on the infrastructure. And all of these pain points can be addressed by making Kafka faster. And that's why we're here. Let's think about another example or another way how to make our Apache Kafka deployment faster. You might be thinking of why we're here. Azul is a Java company, and I'll be talking about it in a minute. But how does it relate to Kafka? So Kafka is written in Java/Scala, and as such, there is a middleman when you're running it on your server. There's a middleman that actually executes the Kafka code on the CPU, and that middleman is a Java virtual machine. It's a middle layer that actually executes the Kafka source code. When people say Java, okay, interestingly, sorry for the resize. Did you see that? Interestingly, when people say, I have Java of this version, they typically mean a build of OpenJDK. That's the standard Java, quote unquote, if you will. And we have multiple distributors and multiple vendors that do distributions of OpenJDK. Oracle builds of OpenJDK, Microsoft builds of OpenJDK, Red Hat builds of OpenJDK, Amazon Corretto, and one of the also very popular ones is Azul Zulu. Azul Zulu builds of OpenJDK. That's one of our products that is freely available, without support. But that's a build of OpenJDK. Now, that's what we do. That Azul makes Java. The thing that you can, why we are here specifically today, is to talk about, can we do something on the Java layer that would affect the application performance? And application, by that I mean Kafka in this specific example. So that's why we'll start talking about our second product named Azul Platform Prime. What is Azul Platform Prime? Azul Platform Prime is a high-performance Java, meaning we took OpenJDK, we ripped it apart a little, re-implemented some of the things, and then the value proposition is, if you place the application on top of our high-performance JVM, your Kafka runs faster. It's able to handle more transactions per second. It's able to serve the requests with lower latency. And kind of finishing the trifle of the pain points, you can then think about, reduce the size of the cluster in order to serve the same amount of requests. Obviously, you shouldn't believe me, right? Like this is, I'm biased, right? So let's try to look a little deeper in the JVM. How do we do that? How do we manage to perform this kind of a magic, let's say? Now we're going to go a little bit more technical, but not too much. So in order to understand how we do that, we just need to remind that Kafka runs on the JVM, and the JVM translates the source code of the Java application into a machine code that gets executed in the on the CPU. As part of the translation, there are things that the JVM does to affect the performance of that application, and one of those things is utilizing so-called just-in-time compiler. So basically taking the source code, observing how the application is behaving, and then perform optimizations and emit machine code. Compiler does all sorts of optimizations on the fly, depending on your workload, and that effect can drastically manifest to faster application. And we'll see what specific optimizations the JIT compiler does. Here's a kind of just a technical picture of a flame graph. Flame graph is a representation of the execution profile, like what code actually gets executed. I want to demonstrate an optimization on top of this, so we better learn how to read the flame graph, just in a very basic way. Flame graph is basically depicting the code, the methods that get executed. So in this flame graph, in the example flame graph, the function A calls function B, and the function B calls function C and function D, and function D calls function E. And the top of the flame, the ratios between the highest level depicts how much CPU time is spent in each function. So you can take a look at this. You can on this example flame graph. If you're looking for optimization, if you're looking for or optimizing your algorithm as an application developer, you want to know where the CPU time is spent. You would be obviously looking in the most time-consuming function, which would be in this case function C. That's where the most of the optimization opportunity is. Now, going back, these are actual flame graphs of executing Apache Kafka. On the left-hand side, it's OpenJDK. On the right-hand side, it's Azul Zinc. They are slightly scaled, but that was a different problem in the visualization. The point I'm trying to make in here is that as we just saw in the previous chart, you're always trying to look in the major contributor to the CPU time spent, right? A big chunk on the top of the flames where you would seek optimizations. That's what the Kafka developers would do. They would profile their application, see the biggest contributor there, and try to optimize, come up with a smarter algorithm, some sort of other code level optimization. even if you're not a performance engineer, and you with the knowledge that we just got, if you look at the flame graph, you can see that on the top, on the very top of the flames, there are just a lot of very small, flames. This method contributes to the end performance by 0.001%, another one by 0.02%. There is not a single method, not a single piece in the code that would actually contribute like 50%, or you would spend 50% of the CPU time. Why I'm stressing this out? I'm stressing this out because there is no obvious place for an application developer, and by that I mean Kafka developer, to come, look at that method, and make Kafka faster. It's just not rentable. If they speed up this very small part of the flame graph, they probably wouldn't get much. And here's what the compiler can do. It does optimizations in a different way other than humans. It optimizes every single piece of code. It does various different optimizations to shave a few CPU instructions here, shaves a few CPU instructions in there. But if you do it consistently, if you do it across the board, across the flame graph, across the whole execution profile, you might actually get a very noticeable speed up. And that's where the majority of the speed up is coming from our optimized JVM Azul Platform Prime. Let's go a little bit deeper technically and show an example of optimizations that the JIT compilers do to make the application run faster. One of the most common ones, and or basic ones, if I will, is called method inline. If you look at on the left-hand side, it's the method foo calls some code or executes some code, and method bar basically executes the method foo. What inlining does is that it replaces the call of the second method and directly inserts the code of the first method in the method bar. This is done transparently for you, right? Every compiler does this. Some better, some less. It's an example of an optimization. But what this optimization actually does is that it shaves off the overhead of calling another method, of putting things aside for the CPU. And there are a lot of small steps that the CPU doesn't have to do. In other words, it shaves off a couple CPU instructions and speeds up the code just a little bit. If you look at let's again see it in practice. This is a zoomed in flame graph. So right now we know how to read it, right? There are methods like Kafka handle fetch request that calls fetch manager new context, and that method calls a bunch of different methods, the very top of the flame. This is the result of an execution graph from Azul Zulu, from a build of OpenJDK. That's how the standard Java behaves. So you can see that the fetch manager new context calls 1, 2, 3, 4, 5, 6, 7 methods, and they all do the work together. Let's look at the execution profile of Azul Prime for our high performance JVM. Our JVM is very good in inlining. It does more aggressive inlining, and that's the result on this flame graph. So you can see that the same method, fetch manager new context, no longer calls 7 methods, but just 2. One of them is native, but that's not important at this point. The thing is, we have now just inlined multiple methods in this one time-consuming one, which reduced the overhead of calling those 6 other methods, and that's a speed up. That's we'll gain 0.00 something here. But if you do it for every method like this, if you do it across the board, it actually adds up. Let me show you another another sort of optimizations that the JIT compilers do, and specifically ours. On the left-hand side, on the top, we have a code sample basically that walks through an array and applies a bit mask. We don't need to really go into details. I'll make a point just visually. We are also not trying to explain how to read assembly code in here because we don't have enough time. But on the higher level, you can see the code that Azul Zulu, the open built of OpenGDK, produced. You can see that there are like these two blocks. What they mean is that it reads a value, that's the MOF instruction, it tests, it does the compare, and then it adds it up together. For some reason, the JIT compiler decided to do always like two items in the array, and then jump back and repeat. That's its decision. You know, it's sometimes a black box. It has heuristics why it decided that way, but that's the end result of that code being executed on Azul Zulu. If we look at the code that Azul Prime generates, at the first sight, you know, it's way more complicated. It looks that way, right? It's actually, you would say it's more instructions, right? The truth is, in reality, these instructions are actually way more efficient. What this example is converted to is that it utilizes the latest available hardware features. Like this is an older example, but these are vector instructions of the CPU. So cutting edge instructions of the CPU. And what this code does, it actually puts multiple values on the stack, then compares them all together at once, then adds them all together at once. And it does actually 32 elements in one iteration. The reason why this is cost beneficial is that these vector instructions jump in big pieces. It's more optimized for the memory, for the CPU to prefetch the data, for CPU to predict what instructions will be implemented next, for eliminated misbranches. So it will make the CPU run faster and more efficiently. So the code on the right-hand side is actually way more efficient than the code on the left-hand side, despite how it looks visually. The point, again, that I'm trying to make is that the different JIT compilers come with different outcomes, and those outcomes can have significant impact on the performance of your application. So I'll start kind of like summarizing the takeaways, which I just said. The choice of the JVM can drastically affect Apache Kafka's performance. You can, by improving the Kafka performance, you can address the pain points that we discussed in the beginning, right? The speed. You can make the Apache Kafka cluster handle more requests per second using the same resources. You can also, just by switching the JVM, we're not talking about application level code changes, right? We're not talking about anybody like application developer doing a thing, really. You are able to reduce the response times of individual events. So it will make your customer experience much nicer. Or you are able to reduce the cost of the infrastructure, because with faster Kafka, you don't have to run as many nodes. I have to make this statement. I'm sorry, I work at Azul. I'm proud of it, and I'm the product manager of this Prime. It's the best and fastest JVM out there. I'll just put it like this. The takeaway, another thing is that it's not just for Kafka. It works for any Java application. I'll actually make some more examples that are relevant to the streaming world. One of the most important things is that these are not the optimizations that the developer can do, right? As I showed you on the flame graph, there is no clear optimization or no clear method where the code could be optimized, right? This is optimization on a much lower level. Obviously, you would first tackle your applications from different perspective, from making tuning Kafka to your removing any obvious bottlenecks on the Kafka side. But then tuning Kafka becomes a diminishing returns exercise, right? Like adjusting IO buffer here and number of replicas there. With just the switch of the JVM, you can probably get better speed up in a faster time, like with using less effort. As I said, it's not just Kafka, right? Kafka is usually, Kafka is a message broker, and the message broker comes, processing messages, events, right? As you know, one of the more popular technologies out there that read and write to Kafka and does computation is Apache Flink. We've also had experience with Apache Flink being put on our JVM. We did some benchmarks. We used some of the standard benchmarks called Nextmark benchmarks. We configured it in a pretty large environment. And we noticed on some of the jobs, we were able to get up to like 20-ish% faster execution time. So you were able to process those messages, by 20% faster, which again can be translated to cost reduction. One of the also interesting aspects of our JVM, or how Flink actually behaves, which is not as relevant to Kafka as for Flink, is the usual phenomenon, JVM phenomenon named as warm-up. What it means is that when Flink is processing messages, the JVM actually does the optimization at the same time, right? This chart depicts, the blue line depicts the load, the events flowing, and Flink doing the computations. The pink line depicts how the JIT compiler is progressing with the compilations. It's actually doing the compilations as it goes. This is aligned by the time. So you can see visually that while Apache Flink is processing the messages, the JIT compiler actually does its optimization work as well, right? And that's interference. That's interference with the application. That's stealing resources. How it manifests is that you'll see worse performance at the beginning of the run of Apache Flink or Kafka, but that there is not that visible because it doesn't have that many compilation. With Flink, it's way more visible, and you'll see worse performance that stabilizes over time, or gets better and stabilizes over time. There's a normal OpenJEK, or there's a vanilla behavior on any Java. What I wanted to say that we have also other technologies, not just the JIT compiler, but additional technologies such as Ready Now, where we're able to control when the compilations happen. Actually, we're able to record where the JIT compiler does its work and try to do it as soon as possible before the load starts, right? So just by like shifting the purple line before the load starts, you're going to ensure that your Flink jobs start processing at the top speed or without interference of the JIT compiler. Oh, these logos just got scaled. I apologize for that. Oh, it happened. To reiterate, it's not just Kafka, right? Kafka is a message broker. It's a centerpiece. It's on its own, it doesn't have much value. Things talk through Kafka, right? So you have other technologies such as Elasticsearch, Hadoop, Cassandra, Apache Acebase, Apache Spark, but then also your microservices, your first-party applications that you write. These talk through Kafka, and all of them are running on Java. Choosing an optimized JVM can affect all of those technologies across the board, making the whole pipeline, whether it's data ingestion or data processing pipeline or data storage, or data search, the whole pipeline can be speed up by using a high performance JVM. And we're actually at the end of the webinar. So I'm going to take some time for questions. If you have any question, please write it down in the chat, and I'll be happy to answer it right away. I'll wait for a couple of minutes. At this point, I'm just assuming that we're writing a long question, but I'll wait. Let's say I'll wait for another 3 minutes till 1:30 Central European time, and if no question arrives, I'm going to end the webinar. So you guys have 3 minutes to ask any questions that you want. Oh, I see Q&A in here. Oh, sorry, I didn't notice. I was looking at the chat. Cool. So, sorry for butchering your name, Basarabaya. Are you stopping standard JIT compilation? Basu, thank you. Are you stopping standard JIT compilation and custom code to do the job? I'm thinking whether I understand the question. Are you stopping standard JIT compilation and custom code to do the job? So RJVM replaces the JIT compiler. So we have in RJVM, we don't use the hostpot's C2 compiler, but we have a different one that we call Falcon. It's based on LLVM. So it's not more of a stopping standard JIT compilation. It's different JIT compilation, right? Smarter, quote unquote. The value proposition of it is that we're our JIT compiler is able to produce smarter optimization, more efficient machine code that then translates to these gains. So it's a different JIT compiler. That's the answer. Hopefully I answered. Yeah, okay, perfect. Hopefully I answered the question. I'm going to give it 2 more minutes in case you have any other questions. Thank you for the question, Basu. You're welcome. All right. So, okay. Azure, quite interesting talks. Please continue to sign up. We'll try. Thank you. By the way, it's Azul, right? Not Azure, not the Microsoft Azure. But we actually get that confusion quite a bit. Maybe my Azure shirt doesn't help with the confusion. Thank you very much. So going once, type going twice. All right. Thank you very much, everybody, for attending. Please don't hesitate to reach out to us if you have any further talks, if anything, any further questions. We're happy to, talk to you directly, have a follow-up. I am personally very passionate about this topic, so we can spend hours and hours talking about it. Thank you very much, and have a nice rest of the day.